Hey, welcome back. This is on basic differentiation rules and rates of change. And right, that's what we want to cover today. Sorry, just checking something out. So let's get in there. Okay, now we're going to stop using the old limit. Okay, we're going to kind of throw it in the trash, and what we do is just start memorizing rules. And the first rule is the derivative of a constant. Okay, so the derivative with respect to x of the c thing is equal to 0, it turns out. Okay, we could always go back and prove these things. A long time ago, people had a lot more time on their hands without all the internet and the entertainment we have. So they're able to go and identify all these great patterns that we use. But anyways, let's go back to the limit definition to prove this thing. So the derivative with respect to x of this function c is going to be equal to the limit as change in x goes to 0 of f of x plus change in x minus f of x all over change in x, which is equal to the limit as change in x goes to 0 of, well, what is x plus change in x? So you put anything inside of f of x. If you put 3 in there, you're always going to get out c. If you put 100 in f of 100, that's c. F of 1,000,000, that's c. F of x plus change in x, that's c. Okay, so you could replace f of x plus change in x with c. Same thing for f of x. That's all over change in x. This will be equal to the limit as change in x goes to 0 of 0. Okay, well, technically 0 times 1 over change in x. But for any value of change in x not equal to 0, that value will be 0. Okay, and then the limit of a constant is 0. There's other ways to kind of get some intuition about how these things are working. The line f of x equals c is just a horizontal line, right? And what are we talking about here? We're talking about slope. So the derivative tells you the slope of the curve at any point. So here you can see the slope of this curve at any point is 0. Okay? And hopefully that gives you a bit of intuition. Likewise, you could do the same thing with y equals x, right? And it's going to be called the power rule eventually. But here we're going to kind of look for a pattern. Okay, so this will give you a feel of what it was like to be one of our forefathers playing around with math. Right, so the first one, x, the derivative of just plain old x. Okay, this one I'm just going to go with the well, should I? Yeah. No, let's go with the, well, yeah, sorry, I'm having trouble making up my mind today. Let's go with the limit. Okay, limit as change in x goes to 0 of f of x plus change in x minus f of x over change in x. This will be the limit as change in x goes to 0 of x plus change in x, n for x, minus x all over change in x. And what are we getting? Limit as change in x goes to 0 of x minus x is just 0, so I have change in x over change in x, which is 1, right? Okay, so the derivative of x is 1. Let's go up 1 power. Yeah, derivative of x squared. What the heck is that? Okay, let's see. Okay, so f of x plus change in x, in this case it will be x plus change in x squared, right? Minus f of x, which is x squared, all over change in x. If you FOIL, you'll get x squared plus, I don't know, 2x change in x plus change in x squared minus x squared all over change in x. Boom, boom. Those go away. Limit change in x goes to 0 of 2x change in x plus change in x squared all over change in x. Just change in x goes to 0. You can factor out a change in x. boom, boom. And you're left with the limit of 2x plus change in x, where if you put in 0 for change in x, you get 2x. Okay. Let's do another one. And we're looking for patterns here. Okay. So this one will be the limit. Change in x goes to 0 of x plus change in x cubed minus x cubed over change in x. Okay. So in general, what are we doing? In general, it's going to be something like this. And you don't have to take notes here. You can just kind of watch. Right? This guy, be the limit, as change in x goes to 0 of, well, the first term is going to cancel with this last part, right? So it'd be x cubed plus 3 x squared change in x plus a bunch of stuff with change in x squares, 3x change in x squared plus blah, 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 I'm running out of room, minus the x cubed. Okay, so what I'm saying is that the first term, the x cubed term, and this last term are going to cancel out. And then there's a bunch of baloney in here. Okay, all of these things are going to have factors, more than one factor of change in x. So it's going to end up canceling out with the denominator. And when you take the limit as change in x goes to 0, this thing will end up going to 0. Okay? In other words, it's this guy, this second term, that really determines the derivative. Okay? So in general, if we have something like this, it would be the limit as change in x goes to 0 of x to the n, which will go away because I'll subtract away off at the end, the x to the n. And then there'll be the second term of that thing expanded. And the question is, how the heck do I expand that thing? Well, you have to have the binomial theorem on your side. And maybe that's a little bit annoying, but if you think about it, what it's going to come down to are the sides of Pascal's triangle. And in particular, it's these numbers right here that give you the coefficient on the second term. Okay, so how do I get to the next, what will be the next number then? 1, 2, 3, 4, I think the pattern says this will be 5. So it's always just going up by 1. And in particular, when we have a third power, this becomes a second power. In general, when I have the nth power, this will be n times x to the n minus 1, okay? And that'll be our general formula. Okay. They go over it in more detail in the book, but you have to use kind of Pascal's formula, which is a way of expanding binomials without having to go through the rigmarole, right? So this one represents x squared plus 2x change in x plus change in x squared. So you see the coefficients of those things are from the triangle. And then 1x cubed plus 3x squared change in x plus 3x change in x squared plus change in x cubed. That would just be the same as x plus change in x cubed. Okay, so it's a clever way of figuring out how to expand these without having to go through FOIL and all that jazz. Okay? But at the end of the day, it allows you to see this pattern for powers. Okay? And that becomes the most important rule for us, the easiest rule. If you have something like y equals 5, well, let's not get too carried away, y equals x to the 5th, its derivative, just bring down the 5, so 5x, and then subtract the old exponent by 1. Okay? So if you have y equals x to the 3rd, y prime is going to be bring down the 3, x to the 3 minus 1 is 2. Okay? Okay, and that allows us to deal with a lot of the problems, believe it or not, in the book. Let's take a look at some of them, right? So example, f of x equals -9. So f prime of x, that's a constant, right? So the derivative of a constant is 0. All right, let's try another. F of x equals x to the 12th. Okay. So f prime of x will be, bring down the 12. X to the 12 minus 1 is 11. Okay, pretty simple. How about this guy? Oh, I don't know. You didn't show us how to do radicals. No, I kind of did. You have to have a little guts to pull this off. Just do the same thing, but you're working with a fraction, right? So y equals, because you could rewrite roots as fractions, fractional exponents. So bring down the 1/4, and then you have x to the 1/4 minus 1. 1 is the same as 4/4. And you end up with 1/4 x to the -3/4. Okay. Usually they want you to rewrite it without negative exponents. I don't care too much, but if you need, if you get a teacher who wants that, there it is. Okay. So you can do that with pretty much any exponent you want. There's some books that will go through and kind of prove it for rational exponents and then irrational exponents. I'm not going to get too carried away. I'll just also note you could do it for something like 1 all over the cube root of x. Okay? So you just have to convert it into a power rule type thing scenario. So you could rewrite this as 1 over x to the -1/3. And then you could rewrite that as x to the 1/3. Okay? And then you could do the power rule on it. So you could bring down the 1/3. And then you have x to the 1/3 minus 3/3, which is minus 2/3. Okay? And if you need to, you can write it nice, x to the 2/3. Okay. All right. So the next rule we want is the constant multiple rule. 2, 3. So a lot of these rules follow along with your limit laws. So recall from our work with limits, if you have the limit of a constant times a function, maybe as x goes to 3, I don't know, that's equal to, you could factor the constant out, the limit of the function as x goes to 3. Okay. So now with derivatives, it's the same spiel. So if you want to know the derivative with respect to x of a constant times a function, because this is actually a limit at heart, what do we have? C times f of x plus change in x minus f of x. Oh, whoops, c times f of x. Great. I'll erase that. Minus c times f of x all over change in x. You could factor that c out, right? And then that'll equal c times the limit as change in x goes to 0 of f of x plus change in x minus f of x all over change in x, where all this thing is the derivative of f of x. Okay, so this will equal c times the derivative with respect to x of f of x. Okay, so this then unleashes a whole another set of functions you can take derivatives of. So let's look at some of those examples. Okay. Y equals 5x cubed. Okay. So for y prime, you leave the 5 alone, and then you take the derivative of x cubed. So that would be, bring down the 3, x to the 3 minus 1 is 2. Okay. And simplify that. So y prime is 15x squared. Okay, keep on moving. Let's say y equals 2 over x. Okay. So first rewrite it so you have something you could work with. So 2 over x is the same as 2x to the negative 1. Okay, so don't forget all your exponent rules. But y prime, leave the 2 alone and take the derivative of x to the negative 1. So I'm going to bring down the negative 1 times x to the negative 1 minus 1 is negative 2. Okay. So y prime will be, and then we can multiply this out. 2 times negative 1 is negative 2, x to the negative 2. And if you must, you could rewrite that with the x squared below. Okay. Just change the sign of the exponent and drop it to the denominator. Okay. Let's keep going. So on your video, you might want to pause and see if you could get them on your own, and then watch my answer. So again, we can kind of keep the 4/5 on its own. So you take the derivative and just take the derivative of t squared. So bring down the 2, then you got t, to the 2 minus 1 is just 1. And then if you want to, you can multiply it back out. Okay. Let's get another. Okay. 2 square root x is the same as 2x to the 1/2. So take the derivative, leave the 2 alone. I'm going to bring down the 1/2. X to the 1/2 minus 1 is negative 1/2. 2 times 1/2 is 1. We have x to the negative 1/2. And then it's just 1 over x to the 1/2. And of course you could write that y prime as 1 over square root x. Let's try one more, and then we'll introduce another law. Okay, I'll rewrite it. Into a form I can use the power rule on. Okay. And so leave the 1/2 alone, and you bring down the negative 2/3. X to the negative 2/3 minus 1 is negative 5/3, so you'll get good with fractions. Multiply that out, you get negative 1/3 times x to the negative 5/3 is the same as 1 over x to the positive 5/3. And you can multiply those together. Okay, this is something you'll have to practice because they're going to have a ton of laws being thrown in your lap. I advise you making note cards, with some of the easy ones on there, and just as you're walking around, maybe take a walk outside. You can quiz yourself. I think there's probably derivative flashcards online. If you get an app for your phone, probably somewhere somebody has thought that up. But you got to practice this. Okay, this is not something that you're just going to figure out. Think back to when you learned the multiplication tables. How did you learn to memorize the multiplication tables? This is the same thing, except you only have, a month or so to figure it out. So figure it out. You have to have these rules kind of automatic, and they're not going to go anywhere. You're going to be using these again and again and again and again. Okay. Okay. Some other laws, again, that are kind of related to the limit laws. The first one, the sum and the difference rule. Okay. So basically, if you have the derivative of the sum of two functions or the difference of two functions, then that's equal to the sum of the derivatives or the difference of the derivatives. Okay. So this will allow us basically to take the derivative of any polynomial. So something like f of x equals x plus 11. All we have to do is take the derivatives of the pieces. So the derivative of x, we know from above, is 1. The derivative of 11 is 0. So the derivative of x plus 11 is 1, the slope of that line. So we can extrapolate that to any polynomial now. Sorry, my pen is acting up today. For example, 3x to the 4th minus 2x cubed plus x minus 1. Right? So f prime of x will be 3 times 4x to the 3rd minus 2 times 3x squared plus 1 minus 0. And then simplify. We get 12x cubed minus 6x squared plus 1. Okay, great. Derivatives then of trig functions, how do those work, right? Okay, in order to figure these out, we need some of those limits we had memorized from our last test. So in particular, we need to know that the sine limit is change in x goes to 0, sine of change in x over change in x is 1. We also need the limit as change in x goes to 0 of 1 minus cosine change in x over change in x equals 0. We also need this sine law. I forget which kind of law this is called, but I just know the sign. So this will be sine x cosine change in x plus sine change in x cosine x. Okay, and we'll be able to now cruise in and figure out the derivative of sine. Okay, so note, if f of x equals sine of x, then the derivative of sine will be the limit as change in x goes to 0 of what? Sine, well, f of x plus change in x, which is sine of x plus change in x, minus sine of x all over change in x. Okay. This will be the limit as change in x goes to 0 of, and now I'm going to use my trig identity, this guy that I'm boxing in red, to rewrite this. Okay. So I'll have sine x cosine change in x plus sine change in x cosine x minus sine x all over change in x. And now I want to rewrite it to take advantage of the two limits that I had memorized. Right? So I gotta be kind of careful about how I pull this off. I think if I take this part and then this part, I should be good, right? Okay, so let's look at what those guys are. The middle part, limit as change in x goes to 0 of sine change in x cosine x all over change in x. Okay, so again, that was from the middle. That was this part. I'm circling in blue. Okay. And then I'm going to go with a minus. So I'm going to factor out a negative from the outer two pieces. We got change in x going to 0 of sine x minus sine x, cosine change in x, rather, all over change in x. Okay. So again, that was from this part. These two pieces I'm circling now in red. And I factored a negative out. Okay, so again, what am I trying to do? I'm trying to exploit those two limit laws at the top there that I have memorized, that I'm circling in yellow. or boxing in yellow. So the first limit on my difference below, I can take advantage of the first limit law, the sine change in x over change in x, and the second one's the other one. I just have to factor out a trig function. So in the first one, I'll factor out a cosine x. Okay. It's not dependent on change in x, so you could treat it like it's a constant and just factor it out of the limit. Okay, so you get sine change in x over change in x, which of course is 1. Then minus, in the other limit, I'm going to factor out a sine x, right? So I factor out a sine x, and I have the limit as change in x goes to 0 of 1 minus cosine change in x all over change in x, and that limit is 0, right? So it's cosine of x times 1 minus sine of x times 0, which of course is just cosine x. Okay, that's the derivative of sine of x. So if you have f of x equaling cosine x, whoops, sine x, sorry. F of x equals sine x, its derivative, f prime of x, is cosine x. If you have f of x equaling cosine x, is its derivative sine x? No, you would be wrong. Its derivative turns out to be negative sine x. Okay, the derivatives have kind of a cool, if you kept taking derivatives, and we'll talk about, if you take the second derivative, so taking the derivative of sine x, leave the negative alone, and then the derivative of sine is cosine. And if you took the derivative again, what would you get? Well, the derivative of cosine, leave the negative alone, and then the derivative of cosine is negative sine. And then if you take the derivative again, derivative of sine x is cosine x. So where did we end up? We ended up right where we started. Okay. So they have the circular nature to them, like a clock. So you could make a little picture if you want, cosine x, and if you take its derivative, you get negative sine x. If you take its derivative, you get negative cosine x. And if you take its derivative, you get sine x. And of course, if you take its derivative again, you get cosine x. So derivative wheel. Okay. We'll need to go in reverse through the antiderivatives in the second half of our class. So, another reason for learning these very well is that eventually we'll be expected to go backwards. Okay, find the antiderivatives. And if you don't know how to go forwards, you ain't going to be able to go backwards. Okay, so again, another reason for learning these very well. So an example from the book. Let's say we have some function g of t equals pi times cosine t. Okay, so g prime of t, leave pi alone and take the derivative of cosine. Okay. You want to simplify this by bringing the negative out in front. So pi times negative sine t is going to be negative pi sine t. Okay. Some reason, I always have a student that wants to write this thing like this. That is bad, because that looks like you're taking a difference. That looks like it's pi minus sine of t. If you do that on the test, I don't care if you know what you're doing or you don't, I'm going to mark it wrong. Okay, that is way out there. You can't do that. It's like using a comma instead of a period when you're writing English. It's a huge mistake. You don't do that. Okay. Okay. Derivatives of exponentials. Okay, so eventually you're going to be working with these problems called differential equations. So you'll want to know things like what function exists such that when I take its derivative, I end up with the exact same thing. Okay, we kind of have seen this play out with the trig functions, right? What function such that when I take its derivative, I get, well, let's say the second derivative. If you do it twice, you put a little 2 here. And you put a little 2 here. Okay, so if you do it twice, what function equals itself, kind of? What function is the negative of itself? Right, we kind of cheat a little bit and look up there. If you take cosine's derivative twice, you'll get negative cosine. So the solution to this differential equation would be y equals cosine. Okay. So you play that game, and it's called, like I said, differential equations. Right? It's important in modeling because if you have situations like the rate of change is proportional to the population at any given time t. So if you're talking about a spread of a disease, if you have a lot of people at like a party, the spread of disease is going to be faster than if you had only like 2 or 3 people. That's saying that the rate of change of the spread of disease in a population is proportional to the population. That's kind of what this equation right here is saying. Is there a function such that its slope is equal to itself? You know, somehow when the population goes up, the rate of change goes up. Okay, the slope increases as the population increases. Is there a function like that? And can you think of it? Whenever they describe diseases these days, they say it has some kind of growth. It's exponential growth. Okay. So the derivative of the exponential is just going to be the exponential. Okay. And that's what that thing says. The rate of change of the population is equal to the population. Okay. Okay, so the more people you have at your Sturgis rally, the greater the spread of the disease. Okay, and that Sturgis rally we just had recently was kind of a major spreader of disease. So anyways, let's look at an example where we're taking derivatives. F of x equals x to the negative 2 minus 2e to the x. Okay, so f prime of x, first I do a power rule on the first guy, so bring down the negative 2. X to the negative 2 minus 1 is negative 3. On the second guy, leave the negative 2 alone and take the derivative of e to the x. The derivative of e to the x is e to the x. Okay? And that's pretty much it. You could, if you don't like those negative exponents, like you've sort of been trained to get rid of them, you could write it like this. Okay. Okay. The final thing they talk about in this chapter in the book is the average rate of change versus instantaneous rate of change. And I've already talked about this a little bit. I'll talk about it more again. I ain't going to kill you, listen to it again. So when I introduced the derivative, I talked about average velocity versus instantaneous velocity, right? So maybe I have some point t and then some point change in t, and this is a position function, s of t. I could figure out the average rate of change going from t to change in t by using the formula. So I'm calling this average rate of change, or I should call it average velocity. So let me change it, average AVE velocity. Okay. So the average velocity is just from the slope formula, s of t plus change in t minus s of t. Okay, so this point right here is, this should be t plus change in t. This point here is t plus change in t, comma, s of t plus change in t. And then this point here is t, comma, s of t. Right? So to figure out the slope, it's just y2 minus y1 all over t plus change in t minus t, which will end up being change in t. Then if I want the instantaneous velocity, you take the limit of that thing as change in t goes to 0. Right? So it'd be the limit as change in t goes to 0. I'm trying to write change in x. Of s of t plus change in t minus s of t all over change in t. Okay. So the difference is, all right, I'm driving to work every day. I got an hour commute. On average, I probably go about 35, 40 miles per hour during my commute. But truthfully, I don't go 35 to 45 miles per hour the entire way, right? That's just my average. My instantaneous velocity, like when I'm on 480, I'm probably going 65 at time, whatever. You know, when I'm in the city, I'm probably going like 5 miles per hour if you caught me at the right second, right? So that's the difference between the average velocity, the overall speed, and the instantaneous velocity, the velocity right at that 1 second. Okay, right. So very important in math and physics, and in general, we have a nice formula, which once we get to antiderivatives, we'll be able to actually construct based off gravity. But in general, in physics, you get this formula for position. Okay, so the position of a projectile at time t is going to be 1/2 times the gravity constant times t squared plus v sub 0 t plus s sub 0, where of course again g is the gravitational constant, so that'd be like what is it, negative 32 feet per second squared, or negative 9.8 meters per second squared, I believe. It's been 20 years since I took physics, so I apologize if I got those wrong. V sub 0 is the initial velocity, how fast it's going when you shoot it out of your gun or drop it off a cliff or whatever. S0 is the initial position. And in baseball, you know, usually the ball is like 2 feet above the ground when it's hit. So that would be the initial position. And if you watch baseball, they even talk about initial velocities as well. So like 101 miles per hour off the bat would be pretty fast, right? 110, 120 in there. So you could analyze that. NASA used to have a website where you could go and look at the physics of baseball, which was kind of interesting. I don't think they have that site anymore, though. Anyways, let's look at an example of these kind of problems. In particular, dropping a silver dollar off a building, which you should not do. If you ever go on Mythbusters, they'll talk about that phenomena. Please do not do that. So you have a silver dollar, and you're dropping it off a mountain or a building or whatever. And the building is 1,362 feet tall. Okay. We'll need a gravitational constant then of negative 32 feet per second squared. Our initial position, well, the initial velocity, first off, we're dropping it at time 0, the speed is 0. So it's going 0 feet per second. The initial position, it's 1,362 feet above the ground. And from there, we can get our position formula. So S of t will be 1/2 times negative 32 is negative 16 t squared plus v sub 0 t, which is just 0. And then plus s sub 0, which is 1362. So that's our formula. The first thing they kind of want to know is the velocity function. So all you have to do is take the derivative, believe it or not, to get the velocity. Okay. So if I did not mention it before, well, I guess it is kind of mentioned up here. S of t is a position function. And then average speed is, you know, usually we introduce st1 minus s of t2. S of t2 minus s of t1 over t1 minus t2. Okay, but we're using t and change in t for t1 and t2. Well, t and t plus change in t. So our, and this should be t2 minus t1, all over the place, I'm sorry. So t2 is t plus change in t, and t1 is just t in our case. Okay, so it's the derivative of the position function is the velocity. Okay, Okay, so if you took the derivative of the position function, you get negative 32t plus 0. Okay. And that's, for velocity, I usually write this cursive v. That looks like that. Okay, what's the average velocity? So so these are all questions and some weird question I found in the book. Find the average velocity on the interval from 1 to 2. Okay, so our average velocity, we have to go to the slope formula, is going to be s of 2 minus s of 1, so t2 minus t1. So this is t1, this is t2. All over t2 minus t1 is 2 minus 1. And then you just plug those numbers into the formulas. So you're going to get, if you plug 2 and 1 into this guy I just put in the box, and do some quick calculations, you get 1298, and then the next guy minus 1346 all over 1. And so my average velocity in that time span is negative 48 feet per second. Okay. Find the instantaneous velocity at t equals 1.5. Well, no, let's find the instantaneous velocities at t equals 1 and t equals 2. Okay, instantaneous velocity then is this v function that we found by taking the derivative. So I need to find v of 1, so I plug 1 in for t, and I'm getting negative 32 feet per second. And then you can plug 2 in for t, so the velocity of time 2 is negative 32 times 2, which is negative 64 feet per second. Okay, they want to know how fast this thing is going when it hits the ground. Okay, so part D, find how fast the object is moving when it hits the ground. Okay, so first I have to find the time, because the velocity function requires a time, and then I have to put that into the velocity function. Okay? So I use my position function and set it equal to 0 to find the time. So I set 0 equal to negative 16t squared plus 1362, because that's the position when the object hits the ground. The position is 0. Okay, well, so solve that for t. You can add 16t squared to both sides. Divide both sides by 16. And you get 85.125. This should be a 2. Take the square root of both sides, and t is approximately 9.23 seconds. Then we plug that into our velocity function. So it's negative, where's my velocity function? Negative 32 times 9.23. Okay. And then that'll equal negative 295.24 feet per second. And that's the speed when it hits the ground. Okay, so good stuff. I'll leave it at that, and we'll see you next time. As soon as I can figure out how to. Use that. Okay, we'll see you next time. Thanks for watching.